Hello students, welcome to video lesson 622. In this video, we're going to investigate the sine and cosine functions a little bit more, and we're going to talk about some formulas that will allow us to do more with them, to find more exact values of sine and cosine, and also talk about why it's actually called cosine, right? We have sine and then we have the cosine. So the question is, why is that? We will answer that question today in this video. We're going to do more of these formulas sort of as we go on. We start with what we call the sum and difference formulas, and then we get to double angle formulas and also half angle formulas. Just different ways that we can use the sine and cosine functions to find more and more exact answers, so that we have to use calculator decimal approximations less. That is the goal, okay? So as I said, we're going to answer these two questions. Why is it called the cosine? Can I find exact values that aren't labeled on our unit circle? In order to do that, if you look on page 291 in your textbooks, you will see a big math notes box that says sum and difference formulas, okay? And it's important to know that something that we actually investigated in our homework from our last video, if you did the bonus question, we looked at this idea. The sine of two different angles, A plus B, we were wondering, is that the same as the sine of the first angle plus the sine of the second angle? Basically, can we distribute that sine piece into the two things that are added together in the parentheses? It turns out we absolutely cannot do that. Okay, the sine of two angles added together is not the same as the two sines added together, but there are formulas for what the sine of two angles added together equals, okay? And they relate to sine and cosine. So you can see here, I have a slightly different version, but your math notes box points out the two angle sum formulas, sine of angle A plus angle B and the cosine of angle A plus angle B. And then it also does the difference formulas when they're minused. A couple things to note and a couple ways to remember these things, okay? If you're doing a formula for cosine, okay, if you're doing a formula for cosine, it's always cosine, cosine, sine, sine. Okay, so it always starts with the cosine that you were doing, the cosine of two angles added together. Cosine, cosine, sine, sine. Okay, and then the symbol is actually the opposite when we're doing cosine, sum, or difference. Okay, so if you're doing the cosine of two angles added together, you're going to do the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second, okay? So the first angle gets cosine and the second angle gets cosine. Those are multiplied. The first angle gets sine, the second angle gets sine. Those are multiplied, and we minus because we were doing A plus B, right? The same is true for A minus B. It's still cosine A, cosine B, multiplied together. Cosines first, sine second, we add those together because this sign is minus, okay? So the sign flips for the cosines. The sign does not flip for the sines, okay? And the angle sum and difference formulas for sine always go sine, cosine, cosine, sine, right? Sine of the first, cosine of the second, cosine of the first, sine of the second. If you were doing two angles added together, those two things get added together. If you're doing a difference of two angles, for sine, it's also a difference of that sine cosine multiplied, cosine sine multiplied. We find the difference, okay? It's important to write those down. I suggest actually writing them on the back of your unit circle. I guess that's less relevant now. It's more relevant when we are all together. So we're just thinking about note sheets and things like that that we can use. But yeah, it's just make sure that this gets down in your notes somewhere, because it'll take a little bit for them to for you to remember what order the sines and cosines come in. Is it plus, is it minus, that kind of thing. Okay, just make sure that they are written down. Now, the first example of what we can do with these formulas is we can actually find the exact value of sines and cosines of angles from the unit circle that we don't actually have labeled, okay? So this one right here says 7 pi over 12. If I draw myself a unit circle, 7 pi over 12, well, if we think about 6 pi over 12 would be a half, right? Would be the same as pi over 2. So that'd be up here. So 7 pi over 12 is just a little bit further than that. Okay, it's up here. It's not quite yet to, the pi over 6, or excuse me, the pi over 3 there. It's not quite to 2 pi over 3, but it's between pi over 2 and 2 pi over 3 at the very top of that second quadrant. So we do not have that labeled on our unit circle, right? There's no coordinate point that we can use to find sine and cosine really nicely and easily. And our calculator, of course, is going to give us a decimal approximation for this. So the only way we have to find the exact value is to try to think of 7 pi over 12 in terms of two things added or subtracted together, all right? And this is where things are a little bit tricky because we have to almost go backwards in our mind thinking, okay, the angles that I have on my unit circle, what values do I get if I add them together? What values do I get if I subtract them? Now, for example, 7 pi over 12, I need to try to convince you that 7 over 12, or 7 pi over 12, is equal to 1/3 plus 1/4. Okay, so if I were to add these two fractions together, their common denominator would be 4 times 3, which is 12, right? 3 times 4 is 12, and this is 4 over 12 plus 3 over 12. Okay, so 4 twelfths, 3 twelfths, that is 7 twelfths. So 7 pi over 12 is actually the same as 1 pi over 3 plus 1 pi over 4. So the sine of 7 pi over 12 is the same as the sine of, in parentheses, pi over 3 plus pi over 4. Do we know the sine of pi over 3 and the cosine? Yes. Do we know the sine and cosine of pi over 4? Yes. So what we can do is we can use this angle sum formula right up here, and we can rewrite this expression in terms of the sine of the first thing, the sine of the second thing, and then plug in our values from the unit circle. All right, so if I were to rewrite this with this formula, it's really the sine of pi over 3 multiplied by the cosine of pi over 4 plus the cosine of pi over 3 times the sine of pi over 4. So now I have 4 things now, right? Sine of this, cosine of that, sine of this, cosine of that. And I know all of those from my unit circle. So I just need to replace these with the values from my unit circle. So the sine at pi over 3, I believe, is radical 3 over 2. Right, radical 3 over 2. That gets multiplied by the cosine at pi over 4, which is radical 2 over 2. Okay, and then I add these two things multiplied. Cosine at pi over 3, I think, is 1/2. And then that's multiplied by the sine of pi over 4, which is also radical 2 over 2. So if I multiply these together, multiply the tops, multiply the bottoms, I think I get radical 6 over 4. And then this one, I think I get radical 2 over 4. Now, it's tempting to say that's radical 8, but it's important to remember we can't add numbers under a radical sign together. We can multiply them, but we cannot add them. So this exact value, the sine of 7 pi over 12, is actually equal to radical 6 plus radical 2 over 4. Okay, because they had a common denominator, so I just used that denominator one time. Okay, so it's radical 6 plus radical 2 over 4 for the sine of 7 pi over 12. So again, this came from the angle sum formula. There is no other way to find the exact value of that. Okay, other things that we can find, by the way, are sine and cosine of pi over 12. Okay, we can do pi over 12. We can do 5 pi over 12. We can do almost all of the over 12s. Okay, so we just rewrite each of these as the sum or difference of our pi over 3, our pi over 4, our pi over 6, maybe. And we can find these exact values that way. That will probably only show up on your test as maybe a bonus question. It's not actually in your homework, but it is one of our most obvious examples of using these formulas. Now we're going to get into problems 82 and 83 on, or in section 622. So they should be probably around page 292, 293, somewhere in there. And number 82, we're going to do just letter A, but then we're going to discuss sort of what it tells us, okay? So what they want us to do is they want us to take this expression, the cosine of 90 degrees minus x. Okay, so now we got to shift our thinking a little bit to degrees, but we're going to sort of rewrite this expression using our formula. And if we have our cosine difference formula written down, that's the cosine of the first part, cosine of 90, times the cosine of the second part, which is x. And now because it was 90 minus x, I'm going to flip to plus. Now I'm going to do the sine of 90 times the sine of x. Okay, so I have, again, these 4 values. 2 of them I should be able to simplify, right? Because 2 of them are just as cosine of 90 and that's sine of 90. If I go to my unit circle, and I remind myself where 90 degrees is, 90 degrees is up here, right? At pi over 2, 90 degrees up. So the cosine of 90 at this value, you could also do this on your calculator if you want. Make sure you switch to degree mode. The cosine of 90 turns out to be 0. Okay, the cosine of 90 is 0. The x coordinate here is 0. That multiplied by cosine of x, 0 times whatever the cosine of x is, really doesn't matter, right? This doesn't matter at all. Because the cosine of 90 is 0, this whole thing is gone. So all I have left is this sine piece. And the sine of 90 degrees, if we think about the y coordinate up here at the top of my unit circle, that's 1. Multiplied by the sine of x, but 1 times the sine of x, so that's just the sine of x. So notice the cosine of 90 minus x is really the sine of x. So the cosine and the sine are the same, except one of the angles was x and the other was 90 minus x. One of the angles was x and the other was 90 minus x. Now, in order to understand why this is called cosine, we need to understand that co, in this case, is actually short for complementary. Okay, and what did it mean when we had 2 different angles and they were complementary? Complementary angles back in geometry class added up to be 90 degrees, right? So if I have a certain angle, let's say that I know it's the sine of 40 degrees. The sine of 40 degrees is equal to the cosine of 50 degrees, right? Because that's what I just found out. The sine of x is equal to the cosine of 90 minus that. So 90 minus 40 is 50. 50 degrees and 40 degrees, if I add them together, they are complementary, right? So the cosine is really short for the complementary sine. So the cosine really means the sine of the complementary angle, right? And that is proven here by this difference formula. Okay, so the same is true, by the way, of the tangents. So cotangent of 90 minus x is equal to the tangent of x. The same is true for secant. So cosecant, the CSC of 90 minus x, that's equal to the secant of x. And we could also show that the sine of 90 minus x, the sine of 90 minus x is equal to the cosine of x. All right? So sine and cosine, they go back and forth with complementary angles, okay? So if I know the cosine of 60 degrees, I also know the sine of 30 degrees. If I know the sine of let's say 45 degrees, I also know the cosine of 45 degrees, right? Those are equal to each other. So that's why this is called the cosine of x. Okay, that's why the whole function is called the cosine. I'll let you sort of prove this one on your own if you want to. Okay, but that sort of gets into 82a and why it's called the cosine. Now, number 83 is another sort of application of this idea of sine and cosine angle sum and difference formulas. This is sort of going to remind us of chapter 4 and even like what we used to do in geometry with trigonometry, with sine and cosine, things like that. We're given these two angles and we're asked to find some things in number 83. Okay, and we're going to go through 83, all the parts, and we're going to eventually be applying the angle sum and difference formulas. Okay, so the first thing that I'm told is that A is in quadrant 2, right? So if I just draw myself a unit circle real quick, quadrant 2, is over here. So in this case, the y values are positive, sine is positive, but my cosine is going to be negative. So the cosine of angle A in this second quadrant is going to be negative something. So I just need to keep that in mind when I do this first thing that I'm going to do. Because part A asked me to find the cosine of angle A. Now your book is using alpha and beta, but it doesn't matter, right? So if the sine is 4/5, right, as a fraction, I want you to remember back to right when we learned about sine. What's the way that we first learned about sine? Well, we learned about it in terms of a triangle, right? In terms of a right triangle and an opposite and a hypotenuse and some old hippies and whatnot, right? So if I say, here's my angle A down in that corner, if I want the sine of that angle to be 4/5, I want the opposite side to be 4 and I want the hypotenuse to be 5, right? Now, based on this information, can we find the adjacent side? Well, yes, because this has to be a right triangle, right, to make my sine and cosine fractions. And because this is a right triangle, I can use the Pythagorean theorem. Pythagorean theorem with 5 as hypotenuse and 4 as one leg is pretty quickly going to lead us to 3 as the other leg. So the adjacent side here is 3. Okay, so, right, because 9 plus 16 is 25. So then the cosine of this angle A is 3/5, right? But remember, because we're in quadrant 2, we have to make it negative. So the cosine of A, which is part A of number 83, is negative 3/5. Okay? And then they ask us to do a similar thing in part B. They want us to find the sine of angle B. And what they tell us is that the angle B is in quadrant 3. So if I know angle B is in quadrant 3, well, quadrant 3 is down here. So both sine and cosine are going to be negative. So this is also going to be negative. And now I'm going to make myself another triangle. And in this case, I'm told the cosine. So I know this is 4. I know the cosine, if I put my B right here, the cosine, the adjacent side needs to be 3. Of course, it's negative. Yeah, I know that. And then I'm going to use Pythagorean theorem again to find this missing side. Okay, now this Pythagorean theorem, a little bit trickier. 3 squared plus x squared equals 4 squared. 16, 9 plus x squared minus the 9, x squared equals 7, so x equals radical 7. Okay, so x equals radical 7. This missing side right here is the square root of 7. So if I write the sine fraction then for angle B, if I go opposite over hypotenuse, I'm going to go negative radical 7 over 4. Okay? So I have now the sine and cosine values for angle A. I have the sine and cosine values for angle B. That means that I have all the pieces for the angle sum and difference formulas: cosine of A plus B, cosine of A minus B, sine of A plus B, sine of A minus B. I can do all of them, right? And that's what they ask us to do in letters C and D. So letter C asks us for the sine of A minus B, right? And if we go back to our angle difference formulas in our notes, the sine of A minus B is the sine of A times the cosine of B, sine cosine, same as this is going to be minus cosine sine. All right. And then I'm just going to replace these four pieces, sine, cosine, cosine, sine, with what I know they are from what I was told and what I found in parts A and B, right? So the sine of A I know is 4/5. The cosine of B I know is, negative 3/5. No, sorry, the cosine of B is negative 3/4. So multiply that by negative 3/4. Okay, and then I'm going to minus cosine of A is negative 3/5. The sine of B is multiplied by negative radical 7/4. So now if I do each of these multiplications, the denominators are both going to be 20, I believe, right? 5 times 4 is going to be 20. And over here, 5 times 4 is going to be 20. This is going to be negative 12. This, a negative 3 times a negative radical 7 is actually positive 3 radical 7. There's a big minus sign between them. So now I can combine the fractions because their denominators are equal. And I'm going to get negative 12 minus 3 radical 7 over 20. Now, of course, here on the top, we could factor out a 3, right? We could actually factor out a negative 3 if we wanted to. But that's not going to cancel with the 20 on the bottom. So I'm just going to leave my answer like this. And I'm okay with you guys leaving your answer like this as well. Okay? But do keep in mind that sometimes we can simplify. Sometimes we can factor out a term on the top, cancel it with the bottom, and so on. Right? And now let's just together go through part D, which asks us to find the cosine of A plus B in this same sort of circumstance, right? So I'm going to go to my cosine sum formula. So the cosine of two angles added together, according to my notes, is cosine A times cosine B. And now I flip the sign to minus, and I do the two sines, A, sine of B. And now again, I'm going to replace these with the values I know from not only what I was given, but also A and B. So the cosine of A is negative 3/5. The cosine of B is negative 3/4. And those are going to get multiplied together. Then I'm going to minus, the sine of A is 4/5. And the sine of B is negative radical 7 over 4. So again, both of these denominators are 20. The top of this one is 9. The top of this one is going to be negative 4 radical 7. But I am minusing these two things, right? So notice that I'm doing 9 over 20 minus a negative. Minus a negative implies that in the end, it's going to be a plus sign, right? So plus, plus 20, and then this says 9 plus 4 radical 7. Okay, so this is the exact value of cosine of A plus B. Notice, I don't even know what A and B are, right? I haven't even figured out what the angles measure. And I don't need to, because I can use these angle sum and difference formulas to find more and more and more exact answers. If you have any questions about angle sum or difference formulas, make sure they're in your notes, and then it's just going to be about applying them, plugging values in, doing the math. Okay, if you have questions, let me know. Please do submit problems 82, 83. Also, of course, I'd like to see, sine of 7 pi over 12 somewhere in those notes as well. And that's all I have for you right now. We will talk to you soon.